Hello everyone. So we have been discussing on plastic deformation under shockwave propagation. So what we discussed in the last lecture is the strengthening mechanisms under shockwave propagation. I mean, under these strengthening mechanisms, so we need to discuss several aspects of it, like several features of it, like dislocation generation, mechanical twinning, or point defect generation, or let's say diffusionless transformation, and maybe some other effects as well. So alloys sometimes contain some brittle phases, alloys containing brittle phases, let's say small phases, or sometimes it may be some particles. So they have they can undergo like strengthening by shock wave, but the strengthening is not much. Low strengthening by shock wave, I will write SW for shock wave, and because due to breakage of the brittle phase, under shock wave, so that means that can generates, I would rather write micro crack instead of crack. So micro cracks, and then micro cracks can lead to failure of the material. Different materials have different strengthening effect by shock wave, like we can write high strength martensitic steel, actually high strength martensitic steel, and ferritic steel. So both of these not significantly strengthened by shock wave. However, austenitic steel is significantly strengthened by shock wave. So there are different types of materials, and they are differently influenced by shock wave. That means the strengthening are different, and because that is probably because of the different strengthening mechanisms. So we will talk about this alloy, the aluminum alloy RMI 38644. So it shows that if we plot stress versus pressure of these alloys, which is from Rec 1976, the reference is, what happens if you want to draw the yield strength? So it will look like this, let's say yield strength, and also ultimate strength also. This trend is kind of similar. So this is with increase of pressure. So what is happening here is, because what lead to this decrease, so we will see the decrease of strengthening reduction. So that this is actually the shock loading, what we are talking about, a very high pressure shock loading. So this is in, let's say, in gigapascal, the unit is in gigapascal, and we are talking about very high pressures, let's say 75, 150, 225, something like that. So, a very high pressure 225 gigapascal here. So this reduction, the early reduction in strength, whether it is yield strength or ultimate tensile strength, under shock wave is due to initial martensitic phase. So initially it is martensitic phase, and that martensitic phase subjected to reverse transformation. That it's not some other phase to martensitic phase, but this is from martensitic phase to other phase. So that's why the yield strength or the ultimate tensile strength decreases, but at higher pressures, that means even higher pressures, that means let us say in this range higher pressures, this will increase, the strength will increase. Why it increase? Because the dislocation strengthening, centering, overcomes the weakening effect, effect due to reverse transformation. The reverse transformation means this reverse transformation what we discussed above, due to reverse transformation. So ultimately the strengthening will happen because dislocation strengthening will be dominant here. So as we have talked about strengthening due to shock waves, so we know that this strengthening can be happen from dislocation generation under shock wave. So that we will discuss dislocation generation, and then there are other defect generation, point defect generation, and then deformation twinning, which we also call like mechanical twinning, and then diffusionless transformations, and maybe some other effects. So these we will discuss. So specifically specially we will talk about dislocation generation, and we will discuss different models, not different models by the way, basically we will focus on one model, but there are other models as well. So how this dislocation generates under shock wave, so that we will discuss now. So this dislocation generation is different in different materials, and dislocation generation also depends on number of parameters, number of shock wave parameters, and some material parameters. So this dislocation generation depends on shock wave parameters and also material parameters, several of the parameters. So for shock wave parameters, we can say that the most important one is pressure, and then we can tell that probably the delta T pulse duration we discussed in the earlier classes. The pulse duration is also important. So the pressure is the most important, most important factor among the shock wave parameters, most important. So what happen is when pressure increases, that means the dislocation density rho will also increase. So Generally it happens that the rho is proportional to square root of P, the pressure, at least up to 100 gigapascal pressure. Beyond that, shock induced heating will affect. Heating effect. So, that means after 100 gigapascal this dependence will be changed. So, but below 100 gigapascal pressure, it is very likely that the dislocation density is proportional to the square root of the pressure. For high stacking fault energy FCC material, so we will discuss about some materials, and mostly it is FCC materials, and specifically right now we want to tell you about the high stacking fault energy FCC metals or alloys, let us say FCC materials we write. So, for example, copper, silver, nickel. So, these type of materials, what happens that dislocation cells can be formed due to shock wave. Dislocation cells formation due to shock wave. We are not going to discuss what exactly dislocation cells, but just to give you the idea. So, what happen is in a material, in a grain, if this is a grain, so there are some cells will form where you have a walls like this. So, wall means this portion have high dislocation density, I would write high rho, that is dislocation density, and inside it has low dislocation density. So, there will be dislocation inside, but the density will be low. So, this is called a dislocation cell. Okay. So, this dislocation cell forms under shock wave, and this happens for these high stacking fault energy FCC materials, and also as we talked about the delta T shock pulse duration also affects. So, what it does is it allow more time for dislocation reorganization. So, rather I would write higher delta T. Higher delta T will allow more time for dislocation reorganizations. So, the dislocation cells, what we have discussed in the earlier slide. So, the cell walls are better defined as this delta T increases. So, as delta T increases, more and more dislocation will accumulate on the walls, and the cell walls will be more prominent. There are differences and similarities between shock induced dislocations and dislocations generated by other conventional means. Shock induced dislocations and dislocations generated by other, or rather I would write by conventional deformation. So, conventional deformation here means let us say mostly quasi-static. Conventional deformation means quasi-static, or let us say other deformations like normal fatigue or creep. So, shock is different, and then we are considering others as conventional deformation. So, we will discuss this differences or similarities. So, what happens in FCC metals means it may include alloys as well. So, the stacking fault energy SFE will determine the dislocation structure in both quasi-static and shock loading. So, this is a similarity that stacking fault energy determines it, and then dislocations are more uniformly distributed in shock induced case, more uniformly distributed in shock loading as compared to other conventional deformation. And then in high SFE alloys, that means high SFE, we are talking about FCC alloys. The dislocation shell walls, I would rather write just shell walls, are not prominent in shock loading, and as compared to others like creep or fatigue. So, the shell walls are well defined, that means more prominent. Similarly, for low SFE, that means low stacking fault energy FCC material, so planar dislocation arrays are generated, and even if it is lower stacking fault energy, so stacking fault SF and twin fault, this is another fault, so twin fault are prominent. Okay. So, then we will not talk about BCC or hexagonal close pack, or let us say intermetallic compound, compounds like in the Merck-Meyer's book. In the Merck-Meyer's book you will get NiAl or Ni3Al. So, these things if you are interested, probably you can refer to to your textbook, or maybe you can search other literatures. So, this is just to give you an overview of different materials have different behavior under shock loading, and there are some similarities of this dislocation generation with the conventional deformation as well. So, some similarities, some differences, but you should understand that shock loading is very different for many mechanisms, deformation mechanisms, the generation of defects are very different sometimes. So, what we will show here is we will show here in a plot. This is the reference is I think more, I forgot the year, though this is the reference. So, that it's a very interesting plot of stacking fault energy and pressure for critical twinning. So, I just write pressure critical twinning. So, this is for FCC metals, So, what we can see from this plot, so that this plot shows that these FCC metals will lie around this line. So, let us say we have some 304 steel here, this is 304 stainless steel, or I would just write SS 304 this point here, and then let us say this one is Inconel 600. Then let us say here we have copper, here we have nickel, and then somewhere here it will be aluminum. So, what happens is, so as stacking fault energy increases, that pre-critical that is pressure for, or we should write just critical pressure, critical twinning pressure. Okay. So, so from this we just want to show you the different substructures. The word substructures, I think I have already told you, the substructures means when we call microstructures, that is that includes all, but when you call substructures, this includes let us say dislocations or other defects. So, these substructures words you should understand. So, here we will show different types of substructures these FCC materials undergo, and these critical the twinning pressure is it's high pressure. This will be 10 these are in gigapascal, it's gigapascal. So, it is let us say 10, 20, 30, 40 or something like that. So, and here also this unit of this stacking fault energy will be millijoule per meter square. So, it is like 150, 100, 200, something like this. So, what we need to understand here that, so why we are drawing this, so this area, around this area, this will be stacking fault area, stacking fault, and if you go higher here, so this will be dislocation cell. That means if you have a high stacking fault energy and the dislocation cell will be generated, but then again if you are going on the other side, right side of this probably line, so you will end up with twin. At high pressure you will get twin, and then for lower pressure you may get the twin faults. So, whether this twin or twin faults will fall here or here, dislocation cell or stacking fault. This is just to show you what are different substructures at different different value of stacking fault energy with critical twinning pressure. So, these are all about we are talking here about shock induced substructures. So, when you call microstructure, that will give probably the mostly the grain structures and then other particles, precipitates or dispersed particles or inclusions, all includes I mean microstructure includes all of them, and then the substructure means inside the grain. So, what we will see like dislocations or other point defects or maybe some twins. So, these are called substructures. So, now there are different models of dislocation generation. So, several models were proposed for generation of dislocations, under shock loading. So, the very pioneer in this field is Smith's model. Smith's model proposed in 1958, and then Hornbogen's are proposed slightly after that, 1962, and then we will discuss in this a lecture about little bit about Mayer's model, that is proposed I think in year 1978, and there are other models as well. So, what we will discuss today is Mayer's model. So, that is called as homogeneous dislocation generation. This Mayer's model so what it says is what are the essential features are, it says that dislocations, I would just write dislocations like this, dislocations are homogeneously nucleated at shock front. When I say at shock front, it can be very close to the shock front as well, and by deviatory stresses. Deviatory stress, this is set up by uniaxial strain, that that uniaxial strain is the characteristic of the shock waves. And what happens, the generation of dislocation. So, this generation of dislocations relaxes the deviatory stress. Okay. And number 2, these dislocations move short distances at subsonic speeds. So, why we are discussing here the Mayer's model, and we are not discussing about the Smith's and the other model Hornbogen models, because they have several limitations. So, I will just go back to that. So, these models have several drawbacks. and there are more models, so we are not discussing, and we are not discussing much about the what is not there in Meyer's book, but the early models have several drawbacks, and Meyer's models try to address that, and especially what we in this model, this is at the it talks about the subsonic speeds, but according to the Smith's model there are some supersonic dislocations, but that was eliminated by Meyer's model. And number 3 is new dislocation interfaces. Interfaces are generated under shock wave. So, what is these dislocation interfaces? We will see in a diagram now, and then so we will just see with a diagram that is taken from Meyer's book, but that is not very perfect here, but just we will see here this is number 1, and then we will go this way after some deformation, this is number 2, and this is number 3, and this is number 4. So, and then this is number 3, and then we will go this way, this is number 4. So, what happens, if you can understand here, there is some changes. This is the shock front, this is the shock front. So, the shock is coming from this way, this is the front. So, you can see that this is the compressed region, compressed, and here it is uncompressed. Similarly, in the second stage, what we can say that this is uncompressed, this is compressed region, but in the stage 2, what is happening here is there are some dislocations generated. So, what happens here, and the dislocations are generated here, but the first we should I just need to tell you that for uncompressed material this lattice was cubic. So, you by now you have understood, these are what we are drawing, these lines are, these are lattice actually, this these are lattice, the atomic planes we are drawing, and so, and then here what happens is these lattices in the compressed region are monoclinic lattice, monoclinic because of the deformation. So, here it is cubic in this region, and here it is monoclinic. So, will the stresses will reach above a threshold level. So, so the stresses above threshold, okay, will generate dislocations. Okay. So, this is the generation of these dislocations. You can see the extra half planes here, also these extra half planes, here extra half planes. So, the planes are not continuous, these are all dislocation, the green ones, these are all edge dislocation you were showing. So, and this is called dislocation interface. So, dislocation interface, what is dislocation interface? This is an array of dislocations that accommodates the differences of lattice parameters between the compressed and the uncompressed materials. So, this is essentially a array of dislocations. So, these nucleation mechanism, dislocation nucleation mechanism is different in shock loading than that of conventional deformation. As you know what is conventional deformation by now. Conventional deformation, okay. And then what will happen is in the third case, so this is our dislocation interface, this is the interface we have, and then the shock wave, shock front will be here, shock front, shock front will advance, that will be ahead now, ahead of interface, ahead of interface. So what happens is, this is what we got, these are some dislocations, we are not showing the dislocations. What happens, there are interface, dislocation interface here, there is a dislocation interface here, there is a dislocation interface here. So what will happen when the stresses at this point will be above the threshold, so then again there will be dislocation generated here. So that's what we are showing, that dislocations will be generated this point as well, okay, and this is already there. So and there will be dislocations here as well. So what happens is, the front is here and this portion is the compressed zone, and then there will be a the rear friction zone here, and then so that means there will be several layers of interfaces. So several layers of these interfaces will form. So this way it will move forward in this direction. So there are several arrays of or several interfaces of dislocations while the shock wave will propagate, move. So with that, so we are closing today. So what we discussed is the dislocation generation mostly in today's lectures. So dislocation generation in shock loading is different than dislocation generation in conventional loading like quasi-static loading or any creep or fatigue. So so there are different models which were proposed, which addresses this dislocation generation and movement during shock loading. Out of these we are discussing about the Mears model, and then we will continue these discussions in the next lecture. Thank you.